In the following few minutes, we're going to make a very brief introduction into classical mechanics and forces and motion. Let's begin with a historical overview. In ancient Greeks' time, the relation between forces and motion was first noticed and stated by Aristotle in his work Physics, and it can be summarized with a simple statement: motion requires force. Which is practical, because if you have a cart, for example, and you want it to move with a certain velocity v, you also need a horse, something that would apply a force F to it. And as long as the force is applied, the cart is moving. As soon as the horse stops, the cart also stops. But of course, this view is wrong, and we actually know kinds of motion that is possible without any external force. Probably the best example is the motion in space, where objects are isolated from external forces with some approximation, and once accelerated to a certain velocity v, they continue propagating continue moving without any external force applied, which is nice because you just need to accelerate once to get to Mars, for example, and then decelerate, and you can save fuel. But it also means that, for example, if you want to accelerate in space, you need something to push off. And if you ever go into space, don't forget to bring something heavy with you, like a hammer, for example. Okay, so this new view on the relation between forces and motion was combined and stated by Newton in his famous Newton's laws of motion. Let's state them in a mathematical form. So the first law states that the object is moving with a constant velocity if either there are no external forces acting on it, or all external forces are balanced, which means that the net force is exactly zero. The second law relates the force acting on an object to its acceleration a. Please note that this equation is vectorial, which means that not only the numbers, not only the values of the physical values of force and acceleration are related, but also their directions. And the linear coefficient between them is known as the inertial mass, m. So two important notes. The first one, both laws are valid in only valid in inertial frames of reference, which should be defined by themselves, but it is sufficient to say that, for example, the frame of reference bound to Earth is a good approximation for an inertial frame of reference for basic daily life processes on Earth. The second one is less trivial, and it is related to the field of applicability of classical mechanics. There are two limits where it is no longer applicable. So the two conditions must be satisfied for Newton's mechanics to be valid, to be working correctly. The first one is related to Einstein's relativity theory. So the corresponding velocity of the object must be much lower than the speed of light. And the second one is even less trivial. It says that the characteristic size of the process in the phase space should be much larger than Planck's constant h. So both these conditions will be actually discussed when you begin studying field theory, relativity theory, and quantum mechanics, respectively. Okay, so what kinds of forces are known? Let's make a short non-exclusive list. beginning with gravity, the force attracting two masses m1 and m2, which is proportional to their product and the inverse squared distance. And it's also proportional to the universal gravity constant G. Then there is a similar Coulomb force acting either attracting or repulsing two electric charges, Q1 and Q2, which is also proportional to their product and the inverse squared distance between them. Then there is a corresponding force related to the magnetic field, known as the Lorentz force, acting on electric charges. Then there is reaction, the force acting on two objects, solid objects, in mechanical contact, preventing them from passing through each other. There is tension, elastic tension proportional to elongation of, say, an elastic spring or a rope, according to Hooke's law. Then there is friction, which also comes in different kinds. For example, this is a formula for dry friction, proportional to the force of reaction N. Then there is viscous friction, which is with some approximation proportional to the velocity of an object propagating in some viscous environment. Then there is the force of pressure, proportional to the pressure, which is basically the driving force of pneumatic devices. Okay, so almost all mentioned kinds of force actually belong to the same basic type of interaction. All of them except for one, for gravity, which is by itself a basic type of interaction. In fact, all the others have electromagnetic origin, electromagnetic nature. So they fall into one category of basic types of interaction. They can be reduced to Coulomb and Lorentz forces. And actually, there are two more basic types, strong and weak interaction, that you will learn about from quantum chromodynamics and nuclear physics later. So since we listed kinds of forces, let's say a few words about acceleration, which is linked to the force. So it's a purely mathematical or geometric description of motion. It's kinematic value. By definition, it is given. It is represented as the first derivative of velocity with respect to time. So it's the speed of variation of velocity. Velocity, on the other hand, can be expressed as the integral of acceleration over time with the reverse operation. The same applies to the pair of velocity and radius vector, the position of the object. So velocity is the first derivative of the position, the radius vector in time, and radius vector is the integral, can be found as the integral of velocity over time. So if you know the forces acting on the object at any point of time, you can reconstruct its trajectory, or you can reconstruct its motion. You can find its position at any given point of time. For example, in the case where the acceleration is constant, these integrals can be easily taken, and then the radius vector as a function of time will be given with this simple expression in the form of vectorial equation. This equation can be projected using a system of coordinates, and it can be represented as a system of equations on the coordinates. For example, this will be the equation on the coordinate x. You can write down the similar equations for the coordinates y and z. Let's solve a simple example to show what kinds of problems you can solve knowing only this. Let's consider a cannon shooting a cannonball with a certain velocity v naught, initial velocity v naught. Let's define the angle at which it shoots the cannonball as alpha. It's the angle to the horizontal line, to the Earth surface. Let's neglect its curvature and say that it's flat, some approximation. And let's also introduce a system of coordinates x and y, with the origin, with the center exactly at the point where cannon stands. So the cannon will follow some trajectory and will eventually fall down onto the Earth surface. Let's see if we can find out what would be the trajectory. So we know that there is only one force acting on the cannonball, which is the force of gravity, directed at the center of Earth in our coordinates. This direction will be the direction down, perpendicular to the Earth surface, and the force can be represented simply as the product of the cannonball mass and the gravity constant g, which combines the mass of Earth, its radius, and the universal mass constant. For us, it is important that g is a constant, which means that combining this with the second Newton's law of motion, we can notice that a is also a constant, which is exactly equal to g, which means that the cannonball motion is uniformly accelerated. And this means that we can write down the equation of motion for it in the form of a system of two equations on the coordinates x and y. Now note that g only enters the equation of motion of the equation on the vertical coordinate y. Now we can exclude time from this system of equations. For example, we can express t from the first equation in terms of coordinate x, and then substitute it into the second equation on the coordinate y, and we get the relation between the two coordinates y and x. Actually, geometrically, this is an equation of a parabola. So it means that the trajectory, with some approximation neglecting friction, viscous friction in air, the trajectory is parabolic. Let's see if we can also find the distance covered by the cannonball. To find it, we must find the second point where the cannonball crosses the line y equals 0. So the condition on the point where it falls onto the Earth surface is y equals 0. So substituting y equals 0 into this equation and solving this as an equation on x, we immediately get the answer on x and the distance itself. So we also can apply the trigonometrical relation that 2 times sine alpha times cosine alpha equals sine of 2 alpha. And this way we get this short, simple answer. From this expression, we can notice that we can, for example, find the maximal possible distance covered by the cannonball. So since sine cannot exceed 1, the maximal distance is exactly v naught squared divided by g. And it is reached when alpha is exactly 45 degrees. So if you want the maximal distance, the cannon must be at exactly 45 degrees to the horizontal line. So this is a kind of problems you can easily solve knowing just Newton's law of motion, laws of motion, simple kinematics, and a bit of trigonometry. So thank you for listening.